So next we'll talk about studies that use ambiguous stimuli to address the question whether speech is a special type of sound for the brain. And I'm going to introduce you to two phenomena. So one of them is audiovisual integration, which is a really important part of speech perception. And the other one is sine wave speech. All right, so let's meet our ambiguous stimulus, sine wave speech. This is what it sounds like. Okay, so now if you've never heard sine wave speech before, it probably sounds like a weird kind of computer noise, okay? Sine wave speech was first used in an experiment by Robert Ramez, and the study was reported in 1981. And here is what they did. So they had completely naive subjects come into the lab and listen to these stimuli. And so by naive, I mean that they didn't know anything about the nature of the stimuli or the purpose of the experiment. And these subjects did not think that they were hearing speech. However, if the experimental subjects were told that, okay, here's like a weird kind of speech, they all of a sudden were actually able to understand what it was saying. Okay, so now that was really exciting because it suggested that maybe our brains have something like a speech mode of processing, like a specific kind of mode into which we can go, and then the speech mechanisms kick into gear and we start perceiving a little bit differently. So that's what made sine wave speech famous and exciting, and it has been used as a stimulus in experiments ever since. Okay, so here I have the same sine wave utterance. Okay, and now I'm going to play the natural utterance that was the source of that sine wave utterance. So you can turn any natural utterance into its sine wave version by messing around with the properties of the sound. So here's the natural utterance.
The steady drip is worse than a drenching rain.
And I'll play the sine wave utterance back to you now, and you'll notice a radical change in your perception. So now, if you hadn't heard that sine wave utterance before, there should have been this really robust pop-out effect where you really, the utterance is all of a sudden completely clear. So now here, what I'm showing is the two spectrograms corresponding to these sounds. So again, in the x-axis we have time, on the y-axis we have frequency. The darkness of the plot shows how much power we have at each of those frequencies. And the sine wave utterance is basically just a very impoverished version of the natural utterance, where we basically get rid of all the acoustic detail and just maintain the very kind of coarse changes of the spectrum. And what's interesting is that even though we've changed the signal so dramatically, it's still possible to understand the signal if you have the right kind of top-down knowledge going into the task. Okay, so let's appreciate a few more examples. And so here I want to highlight an important difference. So what Ramez and colleagues reported is that all you needed to know was that the sine wave speech was speech in order to understand it. Okay, so that's one kind of top-down knowledge that you can have. I was like, okay, I'm going to hear some speech now. Let's see what it says. The other kind of top-down knowledge that you can have is not only knowing that it's speech, but also knowing what the utterance is supposed to say. Okay, so if you had the pop-out effect earlier, that was actually a pop-out effect that was caused by the second type of top-down knowledge. So you actually knew what the utterance said. So let's now see if you can understand these stimuli just armed with the knowledge that the sine wave tokens are supposed to be speech, which I've now revealed to you, obviously. Okay, here's the original.
She cut with her knife.
Okay, so now if you were only able to understand the last presentation of the sine wave speech, then your system needed the actual top-down knowledge of what the utterance was. Okay, and that's how it usually works when I do this in the class setting. So people actually need to know the utterance as opposed to just this sheer knowledge that it's speech. So it's not an exact replication of the original Remez findings. Let's take a look at a couple others still.
They're buying some bread.
So you can ask yourself if you can understand it on the first presentation, just knowing that it's speech.
She ironed her skirt. The floor was quite slippery. The kettle boiled quickly. The man's painting a sign.
Okay. If you got better as we went along, then that would suggest that maybe we started replicating the original findings a little bit more robustly if you didn't actually need to hear the original. But now you sort of have an idea of what sine wave speech is like. Okay, so here's then the kind of general logic of these experiments that use sine wave speech. So you have subjects perceive sine wave stimuli either as speech or as non-speech. And then, so now you have the identical physical stimulus that you're either perceiving as speech or as non-speech. And then you can study some aspect of processing under those two circumstances. And I'm going to give you two examples of these types of studies. And the first one is just a quick one where we learn what is the sheer effect of perceiving a stimulus as speech versus non-speech. So no fancy manipulation, just like what does it do to your brain if you're perceiving something as speech as opposed to non-speech. So this is a study by Riikka Möttönen from 2006, a fellow Finn. And so here, I'll just walk through the basic steps of the experiment. So here we have sine wave non-words as the stimuli. Okay, so earlier we were listening to actual sentences and their sine wave versions. So now we can also create sine wave versions from non-words. And so a non-word here is a phonological sequence that could be a word in the language, but just happens to not be. So for example, something like "mide" in English, that sounds like a perfectly good English word. It could mean something, but just turns out that it doesn't, at least right now. Like, you know, next week somebody could invent a meaning for that phonological sequence. So that's what the relevant kind of non-word here is. So it's something, it's a phonological sequence, doesn't mean anything. And this is a way in which we can kind of like put meaning out of the equation. We're really interested in speech, not in the meaning of speech. So here we have sine wave non-words, so sine wave versions of non-words like "mide" that are first discriminated. So you have two different tokens, and you have to discriminate like which one are you hearing, okay? And the subjects are first thinking that it's just like non-speech, so these weird computer sounds. And then they're told that, okay, actually those stimuli, you can think of them as speech. So they're a type of speech. So now you're in the speech mode. And this was an fMRI study. So you're measuring hemodynamic activity. So no particular timing information of relevance here. And what they learned is that when you're perceiving these signals as speech, that increases activity in the left superior temporal cortex, so around the auditory cortex. So when you think it's speech, your auditory cortex gets more interested in the stimulus. So this is specifically their data. So that's the hotspot in which the signal increased when you thought it was speech. So this is your sine wave speech. The post-training is the data during which they knew that it was supposed to be some kind of a speech. There's also control stimulus that like is completely, nobody's thinking of it as speech. And that's crucial because in this kind of a study, you need to show that the effect is not just an effect of like first session versus second session. So here we can see how much change you would expect just on the basis of first versus second. And obviously the increase for the sine wave stimuli is much, much larger. So that tells us something about just the effect of perceiving speech in superior temporal cortex. So now we can, of course, also study more specific aspects of processing. And the specific aspect here that I'm going to highlight has to do with audiovisual integration, which is a really, really important part of speech perception. So to talk about this, we need to learn about the so-called McGurk effect. So let's first just watch this gentleman articulate. Watch the video.
Ba 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 ba.
Okay. So now if we were actually in the classroom together and I were to ask you, what did you hear? I would get two different types of responses most likely. So some of you would say, I heard da 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 da. And some of you would say, I heard ga 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 ga. So those are the two different types of responses that people would usually give. Personally, I happen to be in the ga camp. That's my percept. Now I want you to close your eyes, okay? Eyes closed, everybody eyes closed. And let's listen again.
Ba 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 ba.
Okay, so now you can hear that actually this guy's clearly saying ba. It's not like a muddled ba or kind of an unclear ba. It's a completely crystal clear ba. So not a distorted sound in any way. So the audio track here is actually playing ba, but what the video is showing is a person articulating ga. Okay, so ba is produced at the very front of the mouth. So there's a bilabial sound. The lips are brought together for the b sound. So it's a very frontal sound. Ga is articulated by making a closure at the very back of our mouth. Okay, so front, back. So those are mismatching here because the visual percept is back, the auditory percept is front, and what your brain does is do a little trick. It's kind of like blending them together so that you get an intermediate percept, which is da, so that's kind of articulated in the middle of the mouth. Or in some cases, like in my case, and maybe in your case, the visual percept sort of takes over and it's like, okay, well, I'm seeing ga, so never mind what the audio track says. I'm gonna go ahead and perceive ga. Okay, so this is multimodal perception. Your perceptual system kind of puts all the stimuli together and tries to construct something sort of coherent from it. Unpack that. So here, when the visual image of a person is saying ga is combined with an audio recording of ba, the percept is da, or for some people, ga. And the kind of remarkable thing about this is that the perception shifts even if the auditory signal is completely clear. Okay, so even in the presence of totally clear signal, this is what happens completely reliably. And so this is an effect that replicates even if you've encountered it a million times. So you actually cannot use your top-down knowledge to kind of stop your brain from having the McGurk effect. Okay, so we can now ask this question like, well, is this something that specifically happens for speech, or does it happen in all types of perceptions? Are we always trying to put together the visual and the auditory perception in this way? Can we get a McGurk effect in other domains? And we know that we can get a McGurk effect in other domains. So this type of integration is not specific to speech. So for example, Saldana and Rosenblum showed already in the early 90s that we can get these kinds of effects for musical instruments. So like during cello playing, you have pluck some bows, and you can mismatch the auditory and the visual stimulus and get a McGurk effect in this domain. So we know that audiovisual integration doesn't just happen for speech, but also for other ecologically valid combinations of auditory and visual stimuli. However, we do also have evidence that there is a difference. So audiovisual integration does seem to be used for speech much more than during the perception of non-speech sounds. It could still be the case that it is particularly important for speech perception. And the evidence for this comes exactly from the study of sine wave speech. So now again, if we want to ask this question, to what extent is audiovisual integration kind of asymmetrically present or asymmetrically robust for speech, we have to find some stimulus that we can kind of move around from speech to the non-speech category without completely changing all the physical properties of the stimulus. Okay, so here's the basic idea of this study, okay? And so now I want to warn you that it's a little bit complicated. And the reason for that is that in order to address the speech versus non-speech question, experimental design typically gets a little bit complicated for all the reasons that we've discussed. It's just a really hard contrast to draw. So what do they do? So here, subjects are always watching videos of a mouthing head. Okay, so that's a bit of a interesting design choice, because in some sense you'd think that just because there's a mouthing head, you'd always be in a speech mode. But it turns out that it did not totally mess up their study. So always watching videos of a mouthing head, and the auditory signal then either matches the mouth movement, so that's your completely natural congruent stimulus, or it mismatches the mouth movement. So that's the McGurk situation. You're like having a mismatching auditory and visual stimulus, and you're seeing how much does the perception shift by function of that mismatching mouth movement. And yeah, so if the mismatching mouth movement changes the perception, then that's exactly the McGurk effect, like when the visual percept is pushing around your impression of the auditory signal. And now crucially, the auditory stimuli were sine wave speech. And specifically, they were again sine wave non-words, and they happen to be sine wave replicates of the Finnish non-words. This is another Finnish team, omso and onso. Okay, so omso looks different from onso because omso includes that bilabial M sound. So it's, you can see that it's omso, and onso does not have the lips coming together the same way. Okay, and crucially, it's sine wave versions of those. And again, it's a task where you have to indicate which one you heard, okay? And this is the crucial part. What you're manipulating is whether the subjects think that it's speech or not. And now the question that they're asking is whether the McGurk effect, the effect of the visual stimulus on the perception of the auditory stimulus, is larger when the subjects think that it's speech. So it does like, oh, this is speech, so now I'm going to be using the visual information more unconsciously. Okay, and the beauty of it, again, is that the physical properties of the auditory stimuli are not changing. So we're keeping the physical properties of the stimuli that change. So there's not going to be an explanation of the results in terms of like, oh, well, now this is like a totally different frequency range. Maybe that's what's causing the results. So let's see what happened. And crucially, there's a natural speech control where we obviously would expect the McGurk effect. That's what happens for natural speech. Okay. The first set of results that I'm showing you come from an auditory only condition. So here we're assessing accuracy when there is no articulatory gesture at all. So there's nothing messing your perception. And here we would expect these are totally clear signals. They're not distorted in any way. Performance should be really good. And it is like, 90 and above for all the three categories of stimuli. So natural speech, that's the yellow bar. Then we have the sine wave speech, either in speech mode, that's the blue bar, and in non-speech mode, that's the gray bar. Okay. So now let's add a congruent articulatory gesture. So here's my congruent articulatory gesture. Congruent articulatory gestures typically aid perception. That makes sense because now you have two different types of evidence for the percept and it all like jives together. It's all congruent, points towards the same perception. And so now all the bars should go up a little bit and they do. Very highly accurate perception. And so now the question that we're interested in, how much lower do the bars go? So how many more? So here we're doing percent accurate for the actual auditory stimulus. How much is your accuracy hampered when the visual percept is incongruent? And so for natural speech here, we're expecting a big effect because we know that the visual percept really affects your natural speech perception. And then what's interesting is to see what it does to the sine wave stimuli, either in speech mode versus non-speech mode. And so in fact, for the natural speech, your accuracy goes way down. And so now what that means in this particular case is that it is a situation in which when the articulatory gesture mismatches, you're going to go with the visual percept, not the auditory percept. So you're only now 3% of this time saying that it is the correct auditory percept despite the mismatching visual perception. And then we have the sine wave data. You can immediately see that they're really different from each other. So when we're in non-speech mode, your accuracy goes down a little bit, but not too drastically. But the effect is much bigger when you're in speech mode. So these are the sine wave stimuli that you're now processing as speech. And here physically, exactly, you're hearing the same thing. But when you think it's supposed to be speech, you're using the articulatory gesture much more. So much bigger McGurk effect when the sine wave stimuli are perceived as speech. Okay, so what's the bottom line? The most important bottom line is that whether speech is a special kind of sound for our brains is a really interesting question, but it's a really hard one to study. And we don't have a clear answer to it. And like I've been emphasizing, controlling the physical properties of signal is always the beast when we're trying to address this question. We need clever experimental design to try to get at it at all. But the data that we have currently does suggest that audiovisual integration could be one of those aspects of speech perception that maybe at least to some extent observed asymmetrically for speech than for other categories. But for the general question, the jury is still out.